Organic Chemistry, Chem 213, Exam 2 material, Part 1. We'll be starting off talking about alcohols and phenols. Alcohols contain an OH group connected to a saturated sp3 carbon. They're important solvents and also used as synthesis intermediates. Methanol, also known as methyl alcohol, is a common solvent, a fuel additive, and also produced in large quantities. Ethanol, also known as ethyl alcohol, is a solvent, fuel, and beverage. Phenols contain an OH group connected to a carbon in a benzene ring. This is the same phenol we saw back when we talked about benzene back in chapters 15 and 16. An enol contains both a double bond and an OH. Note the priority goes to the OH in the last name. One of the things I like about the word enol being used is it shows us that a double bond, or this could also be a triple bond, so a multiple bond, does not have priority over the alcohol. And you will see some examples where the OH is on the same carbon as the carbon-carbon double bond, but keep in mind they don't have to be on the same one. Industrial method for making different alcohols. So I want to take a brief look at methanol and ethanol and their industrial method. Methanol is also known as wood alcohol or methyl alcohol. So methyl alcohol is a name that you are responsible to know. Wood alcohol would be one you'd want to be familiar with. And very small doses can cause blindness, and again, pretty small doses can also cause death. So the industrial method of making this is a catalytic reduction. They take carbon monoxide and hydrogen gas, 400 degrees C, and also metal catalyst, and it forms methanol. Ethanol, also known as ethyl alcohol and grain alcohol. Again, ethyl alcohol would be a name you'd also be responsible for, and grain alcohol would be one I want you to be familiar with or recognize it. Ethanol for non-beverage use is obtained by acid-catalyzed hydration of ethylene, and we can see the carbon-carbon double bond reacting with water under acidic conditions, pretty high temperature, forming ethanol. So if you're wondering how we got the beverage version, keep in mind it's also known as grain alcohol, fermenting grains. Also, we can get wine from grapes, those kind of things. We're going to go on to naming alcohols, but before we name them, I want us to go over the classification of alcohols. When we classify an alcohol, it's classified looking at the carbon that is attached to the OH. So the simplest one is methyl, and sometimes some people will call it a primary alcohol. I think technically it's called a methyl alcohol, but it will behave in reactions like a primary alcohol. The primary alcohol, this is the carbon we're focusing on. It has the OH group attached to it. Notice it only has one R group in this example, so this would be classified as a primary alcohol. Now you don't have to explicitly show your hydrogens, and usually we don't. Usually we show the condensed structural formula. So that's what I have below here. I have the condensed structural formula for a primary alcohol. A secondary alcohol, notice this carbon that has the OH attached to it has two R groups. And again, I've listed its condensed structural formula. And when we look at a tertiary alcohol, notice again the carbon with the OH on it has three R groups. Here's the condensed structural formula. Note that we would never have anything called a quaternary alcohol because one of the spaces of the four bonds is taken by an OH. Just as a reminder, if you're going to label the carbons, you don't have to write out the word primary. You can use the number 1 and make sure you use the degree sign superscripted. That tells us that this is an ordinal number. Using the IUPAC rules for naming alcohols, you select the longest carbon chain, which contains the hydroxyl group, and you derive the parent name by replacing the E ending of the corresponding alkane with OL. Number the chain from the end nearer to the hydroxyl group, giving it priority. And then you number the substituents according to their position in the chain, listing the substituents in alphabetical order as we have in other naming. So as we are looking at naming alcohols, I also want to combine classifying them as primary, secondary, and tertiary. So you'll see my first few examples, I've actually broken them down to primary, secondary, and tertiary alcohols. And then we'll go ahead and practice them again later. All right, the first primary alcohol I'm showing you is ethanol, and we've already seen that one. Next, we have 1-propanol, and I have 1-butanol and 3-methyl-1-butanol. Taking a look at this being a primary alcohol, when you saw the general formula, this was my R group, so my R group is simply just one more carbon. On 1-propanol, you do have to put the 1 here because we do need to tell the reader when they read the name of this that the OH is coming off an end carbon or carbon number 1. Same with 1-butanol, it's coming off of a primary carbon here. And 3-methyl-1-butanol, this OH is coming off of this carbon on the left-hand side. I wanted to give you some examples. OHs don't always have to be on the right-hand side. And then I also have a branch coming off of 3-methyl. You might want to go ahead and draw the structure out or even make the model of it so you can see that even though this name has a whole lot of pieces involved, it is still a primary alcohol. The N-propanol and N-butanol. Before the IUPAC system, they used N to mean something's coming off carbon number 1. And we've seen this lowercase n before. In fact, last semester, they used that to say it was a straight chain. So that's one of the reasons why the IUPAC system came into play, is they needed to be more systematic and not use the same notation for more than one thing. So here I have on this slide secondary alcohols. I challenge you to go ahead and from the name write the structure. Pause the video and come on back and see how you've done. 2-propanol, I have 1, 2, 3 carbons, and coming off carbon number 2 is my OH group. Make sure if you're handwriting this that you make sure the bond goes directly to the oxygen and it isn't bonded to the hydrogen. Sometimes when we handwrite these, we tend to accidentally put the bond not intentionally where we mean it to go. Now there's 2 common names listed here, isopropyl alcohol and rubbing alcohol. They are the same thing and they are also known as 2-propanol. These are 2 common names that you definitely need to know. Isopropyl and rubbing alcohol is so common that if somebody goes into a pharmacy, no one's going to say, hey, where's the 2-propanol? They're going to ask, where's the isopropyl or where's the rubbing alcohol? 2-butanol, in this case, I happen to have my alcohol coming off carbon number 2 of 4 total. Now, I chose 3-pentanol on purpose. I don't want you to confuse the number, in this case 2-propanol and 2-butanol, that actually also classifies it as a secondary alcohol, because even though my OH is coming off carbon number 3, this is still a secondary alcohol. Remember, this is the carbon that we are looking at that is attached to the OH, and on this side I have 1 R group, on this side I have 1 R group, 2 R groups, it is a secondary alcohol. Cyclopentanol, we have 5 carbons in a ring. My OH is coming off any of the 5 corners. So when I write the name, let's say I was given the structure and I needed to write the name, you do not indicate what carbon it's coming off of because it's understood. And let's take a look at classifying this. I have an R group here. This is the carbon with the OH, so I have that R group and I have this R group. That's 2 R groups. The fact that they happen to reconnect on the other side doesn't change that this carbon right here is a secondary alcohol. All right, now we're going to look at some tertiary alcohols. Just as we do with the secondary, I want to go ahead and challenge you to go ahead and draw these structures from the name, pause the video, and come back and see how you did. 2-methyl-2-pentanol, carbon 1, 2, 3, 4, 5. This is written as a line structure. Just as a reminder, anytime you have a bend or an N, you have a carbon. And this is also an intersection. So in this case, we could actually add intersection, but there's a carbon here. 2-methyl-2-propanol. We have 1, 2, 3 carbons with a methyl coming off of 2, and also the alcohol is coming off carbon number 2. This is tert-butyl alcohol. Also, that's its common name. In the lab world, tert-butyl alcohol is what we call it. So this is a common name you want to know. And sometimes instead of tert-butyl, they'll actually just put T-butyl. 1-cyclopentenol. Did you catch this E right here? Now remember, when we had cyclopentanol, we put the OH on any carbon of the 5. But once you put the OH on there, you've now established this carbon right here to be carbon number 1. And then this is telling me in its name that I have a double bond. That's where this E is coming from. Take a look at this. I have a double bond that starts on carbon number 1, and as we know that it always ends on the next carbon, so this would be carbon 2. So 1-cyclopentenol. And then the last one I have on here is phenol, and we've seen phenol before back in the benzene section. Again, it is the same phenol. So what I'd like to do now is I'm going to go ahead and clean up the slides, and we're going to come back and see why these are all tertiary alcohols. All right, checking that this is a tertiary alcohol. This is the carbon that has the OH attached. Notice I have an R group there, there, and there. So this would be classified as a tertiary alcohol. On my T-butyl alcohol, notice I have 1, 2, 3 R groups. Again, this is a tertiary alcohol. Now down here we have, this is the carbon with the OH, but we happen to have a double bond happening here and a single bond here. So when we're classifying carbons, just as a reminder, whenever you have a multiple bond, each multiple bond counts as its own R group. So there's 2 from that side and a third one from this side. So this is a tertiary alcohol. With phenol, we have a similar situation to my previous example. There's an R group here, an R group here, and another one here. Keeping in mind that when you have multiple bonds, in this case a double bond, when we're classifying carbons, each multiple bond counts individually. So this would be 1, 2, 3. This is a tertiary alcohol. So let's put into action what you have learned. If I give you the name, as I did in this box here, here, and here, I would like you to draw the structure. If we have a structure like here, here, and here, I'd like you to generate the name. One thing I want you to look out for is, did you notice in these two that I gave you some geometry? So in this one, you'll be looking for, do you guys remember the R and S? Let's practice on that again. So this one will have to have an R or an S at the beginning of the name. And this is how I show on a ring. I'm showing you that we have a hydrogen on this side of the ring and a hydrogen on this side. So this is where we would include the name cis or trans in the name. So go ahead and pause the video and come back and check your work. So we're going to go ahead and check your names or your structures, and then when we're finished, we're actually going to go back and reclassify all of these alcohols. All right, 2-chloryl-3-pentanol, 5 carbons in our parent chain, all single bonded. So we have 5 carbons, all single bonded. My alcohol piece is coming off carbon number 3, 1, 2, 3. And did you notice because it has 5 carbons, I could have also counted from the other side, 1, 2, 3. And in this case, I put my 2-chloryl, the numbering system that I'm using in my structure is actually going from right to left. And so I have my chloral coming off of number 2. Most likely, and I've got to tell you that if I were to handwrite this, I most likely would have put my chloral on this side. But I wanted you to also to remember that going in this direction would be the exact same compound. All I did was just pretty much flip it over. All right, over here, when you see a solid wedge, dash wedge, typically they're asking for you to include the geometry in the name. In this case, we have a chiral molecule here, so I'll put the asterisk letting us know it's this one. And as a reminder, in ranking for R and S, we go for the highest atomic number gets the lowest number. So oxygen would be number 1. We know hydrogen is number 4. Let's get that one out of the way. Looking to the right-hand side of this, I have a single carbon. To the left-hand side, I have 2 carbons. So we know that this would be ranked as number 2. And this guy would be number 3. So looking at R and S, when the lowest priority is away from you, and that's what the dashed line is telling me, it's exactly what you read. So this would be 1, 2, 3. That would be an S, 2-butanol. 2-phenyl, 2-propanol. Most likely mine is not drawn the way you would draw it, because again, if I hand drew it, I would not be putting the benzene ring first and then adding this to it. I did want you to see though that this is the exact same compound. Remember, it's not an isomer, it's the exact same compound. All I did was put the parent chain on a curve like this. Here's my 2. Here's 1, 2, 3 carbons. My OH is coming off of 2, and my phenol is coming off of 2. Most likely, you would have drawn your prop, and then coming off carbon number 2 would be your OH, and then your benzene ring would be coming off number 2 also, filling in the proper number of hydrogens. So Sorry, you couldn't see that 3 there. So again, most of you probably drew it this way. That is also a correct answer. Okay, cis-2-methylcyclopentanol. Notice my H's are cis to each other, so that's why I have the cis in front of there. This carbon right here has priority. That's the carbon that has the OH on it. So my CH3 is coming off of carbon number 2. On this one, I was reminding you that if you had multiples of CH3 on a carbon like this, that you can go ahead and rewrite it. And instead of having 2 of them coming off, I went ahead and wrote in the branch, and now you could see that it is a propanol. The alcohol is coming off carbon number 1, the methyl coming off carbon number 2. On 3-ethyl-3-hexanol, I have my parent chain here of 6. Coming off of carbon number 3 and 3, I have both my alcohol OH and the ethyl group. So what I'd like to do now is go through and classify all of these alcohols. Coming back up to the top here, 2-chloryl-3-pentanol. This is the carbon that has the OH attached to it. Notice I have an R group to the right and to the left. So this would be classified as a secondary alcohol. Here's the carbon that has the OH attached to it. Here's a hydrogen, so that doesn't count as an R group when we're classifying if it's primary, secondary, or tertiary. I have an R group here, an R group here, so this is a secondary alcohol. So what I'd like you to do now is to go ahead and pause the video, classify the next 4, and come back and check your work. All right, 2-phenyl-2-propanol. Right here is the carbon with the OH. I have an R group here, an R group here, and one here. So this is classified as a tertiary alcohol. Here's the carbon on my cis-2-methylcyclopentanol. It has an R group here, an R group here. It has a hydrogen on that other piece. This is classified as a secondary alcohol. 2-methyl-1-propanol. On the left-hand side, as this is written, there's no carbons there, so that doesn't count as an R group. This one does, so this is an example of a primary alcohol. And our last one has 3 R groups, and this is classified as a tertiary alcohol. For this next section here, what I chose to do was to pull out some alcohols that have a couple of extra things going on. So for the first box on the top here, I have alcohols with multiple bonds. And beneath that, I have how do you handle it when you have more than one alcohol group in a compound. So let's go ahead and start up here at the top. 2-propan-1-ol. This is also known as allyl alcohol. That is a common name for that alcohol. In this case, go ahead and recognize allyl alcohol. I won't have you use that as the name if you were to name something, but you want to be able to recognize that. You might see that somewhere else and you want to have an idea of what's going on. 2-propan-1-ol. So what's happening? 2-propan-1-ol. This 1 right here is telling me the alcohol is on number 1. And this E here has the number 2 in front of the prop telling me where the double bond is. Notice we still have the E missing and we have the OL over here. You have to have a dash between numbers and letters, so there's dashes on both sides. So the reason why they did this is normally we handle both of these groups at the end of the name. For example, we change this to an E to indicate it's a double bond. That's at the end of the name. And also alcohol is at the end of the name. So because alcohol has priority, they go ahead and actually split this up by putting the number of where it's located here for the alcohol. See, it's right in front of the alcohol. And this 2 here is telling me where the double bond is. So now that you've had a chance for me to explain what the pieces mean, I want you to go ahead and pause the video and give me structures for the first 2, and then go ahead and attempt the name for the third one. And then we'll come back and do multiple OH groups in just a second. Two propan-1-ol. In this case, I went ahead and wrote my alcohol on the right-hand side, so my numbering system is going from right to left. The double bond is starting on number 2. Do you guys see that? So this is my structure of 2-propan-1-ol, 2-cyclohexenol. Do you see the double bond here? Because alcohol, when it's on a ring like this, we don't have to give it a number because there's nothing else with it, and it does have priority, so it's understood to be carbon number 1. So this is carbon number 1. And when you draw this structure, once you put the ring on here, I could have gone left or right, so clockwise or counterclockwise. In this case, I chose to go clockwise. And we can see that this is carbon number 2 here. The double bond finishes on carbon 3. 2-cyclohexenol. So for this one, I wanted you to generate the name, but I wanted you to also notice we gave a pattern to it on the first example here. It had a double bond instead of a triple bond, but the pattern would be the same. Priority goes to this carbon right here because it has the OH group. And did you notice that my triple bond starts on carbon number 2, 2-pentyne-1-ol. So now let's go ahead and take a look at compounds that have more than one OH group. The name is changed a little bit. This E is now replaced. It's not removed anymore. And we have the multiplier, in this case 2-di, meaning 2. This is telling me I have 2 alcohol pieces. Remember, with organic nomenclature, they're very good about putting the multiplier exactly in front of what they have more than one of. Now, in front of the name, I'm telling the reader of the name that my 2 alcohol groups are on carbon 1 and 3. The parent chain is 5, and notice it's single bonded. So now that I've explained the name, I want you to go ahead and pause the video, draw the structure for the first one, and then go ahead and attempt the name for the second one. Come back and check your work. All right, this is carbon number 1. Here's 2, here's 3. If you want to go and number all your carbons, you can, but these are the ones that are highlighted the most. I have 5 carbons all single bonded with my OH group coming off of carbon 1 and 3. All right, to name this one, let's take a look at the longest continuous chain, which contains all of the OH groups. My numbering system would be going from left to right the way I have mine written, and that's because the lowest numbers would be given to OH going in this direction. I'm going to go ahead and label this number 3. There's 4. And you have carbon number 1, 2, and 4 with the 3 OH groups. Remember, this E has to be there. And I have 3 alcohol groups. This whole piece right here is the parent name. The substituent that's coming off of it is the CH3, and it's coming off carbon number 3. Naming phenols. The word phenol is both used as the name of a specific substance and also as a family name for hydroxy-substituted aromatic compounds. Phenols are named the same way we learned in the aromatics section. I did want to show you when you have a CH3 group and an OH on the same ring, as we do here in the case of paramethylphenol. I wanted to show you priority still goes to the OH. This is simply a CH3 group. What we're looking at here would be, in a sense, competing common names. We have toluene and we have phenol. OH has priority. So we're going to call this a phenol. And when we look at the rest of the compound here, this is simply a methyl group coming off of it. We can use the ortho-para-meta system of naming. Whenever you have just 2 things coming off a benzene ring, you are allowed to use that. The alternate name for this would be 4-methylphenol if you wanted to use the numbering system. 2,4-dinitrophenol. Here's my phenol group. You could go clockwise or counterclockwise. In this case, I went clockwise. Here's my NO2 group on carbon number 2 and on carbon number 4. If we were to classify these as primary, secondary, or tertiary alcohols, let's take a look. I have an R group here, here, and here. Remember, this is the carbon that has the OH group attached to it. So this would be a tertiary alcohol. And I want you to note that even though I have something else connected to the benzene ring, it doesn't change that this is still a tertiary alcohol. just like we have the same situation happening here. Phenols are always tertiary alcohols, regardless of how many other groups are also coming off of the benzene ring. It's this section here that calls it a tertiary alcohol. So it's time for you to go ahead and draw the structures, pause the video, and come on back and see how you've done. Metachlorophenol, OH group, is on carbon number 1. This chloro is meta to that. On 2,4,6-tribromophenol, this is the carbon here that has priority, so it's always number 1. So in this case, this has to be number 1, so I can either go clockwise or counterclockwise. And this is a symmetrical compound, so it doesn't really matter. I get the same name if I go clockwise or counterclockwise. There's no competing numbers. But take a look at this. If we were to ignore what's on the end of these, it seems like the numbering system, the lowest numbering system, would be going in this direction, giving bromo carbon number 1. But the reason why we don't do just the physical locations to establish the numbers is because we now have a compound, or we actually have a functional group on there that has priority over these BRs. So it has to be carbon number 1. So on the bottom of this slide, I have where the hydroxy group is not priority. When we have carboxylic acids, aldehydes, or ketones, those have higher priority. You have 2 groups that you know already that actually have priority, and that would be benzoic acid and benzaldehyde. Those were 2 common names and structures I asked you to memorize back in the benzene section. So how you would name those, because OH does not have priority, the name would actually be hydroxy for the OH group and still use the priority name of benzoic acid or benzaldehyde. Go ahead and draw the structures, pause the video, and come back and see how you did. All right, meta-hydroxybenzoic acid, my OH group is meta to that. Para-hydroxybenzaldehyde, there's my benzaldehyde group. I have my benzaldehyde group, and para to that would be my OH.